Good.
Okay, yeah, thank you all for coming to the second colloquium of the semester. We're gonna have our own Professor Klaus Volpert talk about dynamic Criterion.
Thanks, Mike. Thanks for coming. This is joint work with Nick Rubino, Maya Ripples. Nick was going to join us for the talk through Zoom. He's just coming in. All right. Awesome. Nick is one of our fabulous graduate students in our department and about to graduate with a master's in mathematics. He had an undergrad degree from Villanova also in finance, and we go way back because he took CAC 2 with me and 3 in PQ and so forth. So we go way back, and it's been a fun collaboration. Maya Repholz, it was a high school student at the time we started this project. She is now a student with at MIT. And yeah, so Nick did practically all of the coding. So if you have any coding questions, it'll be on Nick. Maya was the one, so he's the first author on this paper, and Maya is contributed, among other things, the main theoretical idea that I will talk about. The paper has been provisionally accepted by the American Mathematical Monthly, and if everything goes well, it should appear early next year. Oh, and a shout out also to Jesse Fry, who helped us with this paper early on, and to Joachim Repholz, father of Maya Repholz, who contributed, among other things, the name for the term, dynamic Criterion, and also was a reader of the paper and helpful throughout. All right, so I'm gonna start with a question for you all, for all you gamblers out there. I'm going to ask you a gambling question where I'm going to ask you for a number, a betting size, okay? And I want you to be serious about it and actually really, if you have a piece of paper, write down the number that you would commit to. I really like you to think about it. So here's the situation. Suppose you are given $100 and as a starting capital, and you get to play a game repeatedly 100 times, up to 100 times. Betting a share of your capital each time. The good news is that the odds are in your favor. So we're going to assume for this game that you have a 60% chance of winning, 40% chance of losing. So think of it as a simple coin toss of maybe a loaded coin that comes up 60% heads, 40% tails. So a simple game like that. And the one wrinkle is that you have a maximum payout. So you start with 100 and the maximum payout is $1,000, right? And if you reach that $1,000 before the game is up, you can keep the $1,000, you're done. If you don't reach it, you get whatever you have after 100 games, right? So the question is, how much, let's just say the first game, how much of the $100 would you bet? So here is the game laid out, and I give you a moment to think about it. What proportion of your $100 are you going to bet?
What's the payout?
Good. Great.
If I win, what do I get?
1-to-1, if you bet $50 and you win, you will have 150 after the first game. If you lose, you will have 50 after the.
So if I bet 50 and I win, I get my 50 plus 50.
Correct.
Back. Okay. And if I lose all of it?
Yep. Okay.
Okay, thanks.
right intuitively. So if you have a piece of paper, I would really like you to write it down. If you don't have a pen, write it on your heart. Anybody willing to share what would be there? Yeah, did you write something down? All right, outstanding. Anybody willing to share what they would bet? Yeah, Tim?
It's your money, right?
Yeah. Yes, it is. Yes, it is.
Well, being the rather conservative, and
Yeah.
I don't really like gambling, I don't believe in gambling anyway, I'll say no more than
50 cents.
15 to 20% of my whatever I have.
15 to 20.
So $15 or $20.
Okay. All right, Bob?
60.
$60.
This has something to do with the numbers. There's numbers. So why not?
Okay. Anybody else willing to? Yeah,
36.
36. All right. Jacob, how about you? What would you say? Intuitively, what do you feel like? I mean, some of you might say, I'm not betting more than 50 cents because I'm not a gambler type. 50? 15? 50, okay, all right. Paul, what did you say?
I was thinking 20.
20, all right. Anybody else? Yeah, Bruce?
24.
24, all right, Katie?
Bob's logic, but opposite 40.
40, all right.
I'm slow. I don't think I understand the game still. When you say the winnings are capped at 1,000, is
Yeah.
that each time I bet the winning is capped at 1,000? Or my total winnings all together? are
The
capped at
bankroll,
1,000?
so the $100, you start with $100 and each game you update the bankroll.
So I can never have more than $1,000
Correct. Correct.
or I can never have more than $1,100.
So. Think about it.
Yeah.
Okay.
Well, I was thinking that if I could win 1,000 each time, then obviously if I got to 2,000, I would just keep betting 1,000.
You
All right,
can
we got
never bet
1,000
more than you have, you can never bet, you cannot borrow money.
But yeah,
No
okay.
leverage, no leverage allowed, no. No borrowing and,
Anything it is.
I didn't know that it was like the total winnings or each time.
right.
Okay. Good. Okay.
Yeah, Bob.
I'm a little confused because if you have 100 tries, why
Yeah.
would we blow such a big amount in the first try? I would be more conservative.
Uh-huh.
Like $1, $5 to see what's
Okay.
going on.
Awesome. Yeah, that's exactly what we're thinking about, right? So, you have a limited time and you have that cap, and how do you work with that information in terms of strategy, right? That's what this talk is all about. So the way this came about was a student of mine, Tasha Boland, saw a report where two Wall Street dudes played this game, actually offered this game to 60 or 61 students from a fine business school, shall remain unnamed. And they put real money down. Okay, so this was real money. For them, I guess it was chump change, Wall Street dudes, I guess. But nevertheless, they were willing to put up real money. So the subjects had real skin in the game. They could keep whatever they want, and it was designed to take less than an hour. So they had a chance to, within 1 hour, to earn a fine chunk of money. Turns out they did terrible. They did terrible. Despite the favorable odds, 28%, almost a third, went bust. That is, they lost more than 90% of the starting capital, ended up with less than $10. About 2/3 managed to stay above water. I guess that's good. Only 21% managed to reach the cap. And the average payout.
So those are percentages, not numbers.
They are percentages, yeah. Right, 21% managed to reach the maximum, and the average payout was $364. Now, that doesn't sound very impressive, at the very least, they did better than a random strategy. A random strategy would be like the worst possible strategy, basically just going like, well, whatever, I'll bet whatever. I use a random number each time, uniformly distributed between 0 and 1. Oh, like, oh yeah, I'm betting 90% now, and now I'm betting 10%, and so on. This is a random strategy, again, very easy to implement and code. So with some Monte Carlo simulations, we were able to see what a random strategy would result in. And you can see that 72% playing a random strategy would go bust. Despite the good odds, 70% would go bust, would lose everything. But 27% would reach the max. So you can see, actually interesting, that a random strategy played out over 100 games leads essentially to one of two outcomes. Either you make the max or you go bust. Okay. And the average payout would be 270. And so you see that the subjects just barely beat out the random strategy. So that's pretty terrible. So why did Hagani and Dewey, the Wall Street guys, do this? Besides getting a good laugh, I guess, because they spend much less money, they had to pay out much less money than they thought they would. They wanted to show the difference between intuitive betting and a mathematically driven betting strategy. They suggested that instead of sort of just intuitively thinking about a percentage, they should play consistently a strategy known as the Kelly Criterion. The Kelly Criterion, in this case, with this game, says bet 20% each time. So if you said $20, you're a Kelly guy or girl. And indeed, one can again simulate with this strategy how one would have done. And you can see just how incredibly much better a mathematically driven strategy would be. Instead of, yeah, go ahead.
The numbers add up to 100.
The last number is
Because
included
reaching the
in
max
the
is also over 100.
The third number is included in the middle number.
Oh.
Right.
I had the same question.
Right. So instead of 66% ending above water, playing Kelly has 83% ending above water, meaning ending above where they started. Instead of 21% reaching the max, 58% would reach the max. And I don't know what's more impressive. Maybe the average payout goes from 360 to 680, almost doubling the average payout. Or you might be impressed by the fact that the number of subjects going bust drops from 28 to 1%. Yes.
Would you consider a better strategy? Like, which of those metrics would you want to optimize for better?
That's a great question. Yeah, we're gonna, this perfect segue. We're gonna get to that. Yes. Right. What do you want to maximize? What is actually our main goal? Do we really want mainly achieve a minimum number of going bust? Well, if we minimize the number of people going bust, then the strategy would be do nothing, not bet at all. So we wouldn't do that as a main goal. But it's crucially one part of it that we want to avoid high risk. That's how you would I mean, the whole thing does apply to investing. So when you invest, you think you have favorable odds by going into the stock market or whatever. And you do want your investment to bear a good amount of payoff, and you do want to avoid losing money at which one is more important to you is a little bit a personal perspective, right? Yeah.
Just wanted to, I'm assuming you'll tell us where the 20% comes from at some point. Because we're just taking it on faith that that's the mathematical solution right now.
Really? I need to talk about that? My talk will be that one can actually even do better than this. Okay, so our even Tasha Boland said, like, oh, isn't there maybe possibly a better way? Can we do it better? And she did show that there is a way to improve on that, but she didn't prove that this was the best possible way. And so Nick, Maya, and I took it from there and go like, can we actually prove what is the actual optimal strategy? Maximizing, well, what exactly? But let's just say that we wanted to find an even better strategy than betting a fixed 20% each time. Where does the 20% come from? All right, so let me tell you a little bit about the Kelly criterion. It starts out with a paradox. The paradox is this. At first, we would want to probably maximize our average payout, our expected payout. What strategy would give us the highest expected payout? The paradox is that the math, when we do that, the math tells us to bet everything. Go all in each time. That's what the math says. And I'll show you how. It's really simple. The expected payout is simply, for a given game, is simply the bankroll times F, 1 plus F. F is our, the key variable, how much, the proportion we want to bet. And so if we win, the bankroll goes to P times 1 plus F times probability P, 1 minus F if we lose with probability 1 minus P. If you work that out and then look for the maximum F, you take the derivative of this with respect to F, and you see that the derivative is always positive, as long as the probability is greater than a half. The derivative is always positive. So what is the conclusion? F, the domain of F is 0 to 1. If the derivative with respect to F is always positive, tells you that the maximum occurs at F equals 1, meaning you go in all time. How can that be? I don't know how you can. Because it's true even for 100 games. Even if you play 100 games, the math says go in all the time. And how can that possibly be a good strategy? Well, it's not a good strategy, but the math tells us what the expected payoff would be. And the thing is that even though you go extremely likely bust, with 99.999% chance, with 0 payoff, right? There is this itsy-bitsy chance, to be exact, it would be winning 100 times in a row, which is 0.6, 1 over 0.6 to the 100th, right? Tiny percentage, but the payoff would be astronomical. And when you average it out, you actually reach a maximum. So it's a classic case of, Mike Levitan always makes this comparison with feet being in the ice bucket and your head in an oven and go like, on average, you should feel all right. So, but as a strategy, this can't possibly be right. So the math is correct. So what's wrong? The answer is that we are maximizing the wrong thing. We're maximizing the average payout, which is not the right thing to look at. What should it be? In order to solve this paradox, what should be the thing to maximize?
Klaus, I have a question.
Yeah.
Yeah. Is that the maximum amount, assuming that F is constant?
Yes.
Okay, well, what if it isn't? I mean, you gotta
Okay, great. Andy, you're anticipating what I'm going to talk about. Yes, because we are the optimal strategy will look at what we can do if f is not constant.
Mhm.
Right, but the paradox is a standard paradox. It actually arose some 300 years ago in another paradox known as the St. Petersburg paradox, where a related game is set up, and again, the maximum payout would require that you pay infinite amount of money for a game. And there was a letter exchange between two famous mathematicians of the day. Kramer is a little less famous, but Bernoulli, certainly one of the Bernoullis, I think it was Nicholas. They decided to solve this by looking at the utility function. We want to maximize a utility function. So the utility is the idea that $100, the simple idea that $100 means different amount to somebody who has only $1, relative to one who has $1 million. An extra $100 means very different things to some, So what really is important is not the absolute gain, but the relative gain. That is, you're looking at the ratio of your winnings. And that is what we want to maximize. So more clearly, we want to maximize the expected average return. So think about sort of the random walk our bankroll takes. All right, we start at 100, and then it goes up, and goes down, goes up, goes down, and so forth. What we want to maximize is not the end point. What we want to maximize is the average rate of return. The steepness of that, the average steepness of that. That's what we want to maximize. Okay, that is equivalent in many ways. We can think of it to understand that is to say, when we go from $100 to $200, if you have two people, and one goes from 100 to 200, and the other one goes from 100 to 0, that's not a wash. We think that's a wash, but it's not. That would be a linear utility if that was a wash. But no, what is a wash would be if one doubles and the other one halves their starting capital. It's the ratio that matters. All right. So we're looking at the ratio and thereby maximize the average rate of return. Okay, that is what we want to maximize. In effect, we can also think of it that this logarithmic utility function downweights these astronomical payouts and upweights the ruinous payouts. So you also can think of it this way as a different weighting. When we do that, here's a little bit of math, the only proof of my talk. Don't be intimidated, it's not hard. So just hear me out, Here's the derivation of the Kelly criterion. We start out by saying, all right, the nth, Bn is the bankroll after n games, would be the original bankroll times 1 plus f to the number of successes times 1 minus f to the number of failures, right? And the key function is the average log return. When we plug that in, you can see with the law of logarithms that the s and the f divided by n come down in front, law of logarithms. And when we're playing the game long enough, by the law of large numbers, that converges to the probability of success and probability of failure, respectively. So this is the function we want to maximize. So when we do that, we again use the derivative, set it equal to 0 and solve for f. And this beautiful formula drops out. F equals 2p minus 1. That is Kelly's criterion. So when p is 0.60, plugging that in, we get 1.2, minus 1, we get 20%. So if P is 0.7, say, if the probability is 0.7, we would bet 40% if the probability, and so on, right? And if the probability is 50%, 50-50, we bet how much? That's 0. It's a very moral talk that I'm talking about, okay? If the chances is 50-50, no gambling, all right? Main message. Notice that when we play the Kelly consistently, just to make sure, we've not guaranteed a favorable outcome. The luck of the coin toss can still create a loss, right? So it can, our bankroll can look like this, or our bankroll can look like that. But that being said, the likelihood of a favorable outcome is hugely sensitive to that percentage. Really impressively so. You can see when I graph this expected log return, then it has a maximum for P equals 0.6, maximum at 0.2, and just deviating slightly from that dramatically changes the outcome. So if I bet 40% or more, I'm looking at unfavorable outcomes where losing half of our bankroll is more likely than doubling our bankroll. So the ruinous becomes more and more likely. And that is very much demonstrated by the results that I showed you earlier, that in the experiment, we had so many people go bust. Easily explained, people were too aggressive. They bet too much. All right, so when we play the Kelly criterion, I showed you this before, consistently we have this much improved results. So that is the difference between an intuitive strategy and a math-driven strategy. Main message here.
Moral number 2.
Moral number 2, yes. That's it, very moral. However, what the fixed Kelly doesn't take into account is that in our case, we have a maximum payout and a limited time. And Nick, Maya, and I set out just to see what that extra information can be used in order to improve on those results. The first idea is really very simple, and that is if you're close to the cap, right? Betting 20% might overshoot. So why bet 20%? You're risking things for no reward. So clearly, when we're close to the cap, we should reduce our Kelly. The question is, but if we just do that when we're getting so close to the cap, the improvement is tiny. So the question became, well, can we actually put on the brakes on Kelly earlier? Right? And by how much? And how much would that make a difference? And it turns out, yeah, while it'll improve on this, not as dramatically as this, but still a good notch better. So we started out with thinking backwards. If one game is left, what should be our betting proportion? Very simple. Clearly, if we are close to the cap, by the way, I'm going to switch the cap to 1 so that I think of the bankroll as just a percentage of that 1, so I can leave M out of our formula. So we set the maximum equal to 1 and think of the bankroll as a percentage. If we're close to this maximum, I'm going to just take F to be whatever it needs to get to 1, which is 1 over B minus 1. If I'm still far away, the previous proof of showing that Kelly is optimal kicks in again and says, all right, we're going to bet Kelly. I'm going to call this full Kelly. But as soon as we are close to the cap, the betting goes down like that. Okay. So now here comes the crucial idea. What if we have 2 games left? So here now, this picture shows the bankroll vertically. Now, in the previous picture, I had it horizontal. Here's the vertical, here's the bankroll from 0 to 1 at the end. Now, with 1 game remaining, we had this break into 2 intervals from here to here and here to here. This interval was the one where we are close to the cap, this rarefied interval where we're close to the cap. And these break points between the intervals, we're going to call nodes. And as we move backwards, we get more nodes, more breaks in the interval. The first break occurs where we are still so far away from the cap that even 2 full Kellys will not get us to the limit. So we bet full Kelly. If we are in this strategy, in this interval, we again bet just what's needed to get to the max. The interesting question is what happens in this interval? First off, what should this break be, this node? It turns out that this node naturally is the halfway point between these 2 nodes, because at that halfway point, if we bet the right thing, then a win will get us to that node, and a loss will get us to the other node, right? Because winning and losing is symmetric, so we're getting a halfway point. That was actually the key idea. That is that simple. Just take the halfway point to break the interval. So remember that when we come back. I come back to that.
Because of the slope of f and negative n.
Yes, right. So the win and the loss is symmetric. The way that's how we set it up. If you win, you gain 50. If you lose 50, right? So that's the idea. All right. So on this middle interval, what should be our betting proportion? This gets a little bit involved. We look at a tree of simple binomial tree where we look first as to we start with that bankroll. A win gets us here, a loss gets us here. And then another win here, another loss here, another win here, another loss here. 4 possibilities. The good thing is that if when we are here, we know in which interval we are, we can plug in the proportion that we already figured out when there's only 1 game lost, 1 game left. So this is the 1 over b minus 1 formula, right? 1 over b minus 1 because we are in this interval. And then here's full Kelly because we're in this interval, right? So that gives us this expression. Then we can calculate the expected log payout by taking each of these 4 expressions, multiplying them by the respective probability. So here's the 2 wins. So we get multiply that by p squared, win and the loss, 2 losses, etc. We can maximize that. A little bit of algebra involved. Maple helps if you want. And this comes out to be the optimal strategy with 2 games left and in the middle interval. When I graph this, I get this green line. And what do you notice? You notice that now with 2 games left, I can put on the brakes earlier, right? This when it goes down, this is what I call putting on the brakes. I don't need to bet full Kelly, right? So when I graph this this optimized function, this optimized proportion, I get this green line. You can do this with 3. And then of course the math is hairier, but look at the result. Blue line is now with 3 games left. Again, what you see is that I can put on the brakes even earlier. The point where I deviate from the full Kelly is exactly the point where I can say, all right, with 3 wins in a row, betting full Kelly, I get to the max. So I don't need to, if I'm closer to that than the 3 wins, I can put on the brakes already. And this is the blue shine shows that. Yes.
So this is really a dynamic programming approach.
Yes,
You have a
recursive,
discrete number,
exactly.
right?
So this all ends up with recursive, exactly. Backwards recursion from knowing what we are doing on the last game, we figure out what you need to do with 2 games left. From that, we figure out what to do with 3 games left, recursing all the way. In fact, that's exactly where we're going. The math, the algebra gets hairier and hairier. And we only did it, I think, to 4 and then gave up. And then decided, oh, what we really need to know is, and that's relatively easy, is what is the proportion to bet on the nodes when these intervals break. Let me go back to that graph here. So as I go back, I simply look at 2 nodes, look at the midpoint. And the midpoint is a node, and I know exactly what my betting proportion will be, so that this node maps onto this node with a win. Okay, so I can solve for f really easily on the nodes. Okay, so I don't know, I'm giving up on what f should be in between. But what it should be on the nodes, it's easy. And in fact, it's given by this recursion formula. The nodes are 0 and 1. There's this lowest node, which tells you this is the point with where I get to the max with k straight wins. And the other nodes are simply midpoints of the nodes with 1 game left, less left. 1 game less left, right? And the proportion to bet is just exactly what I need to get from one node to the other. Okay. So the nodes map to each other, and that simple insight allows us now to recursively figure out the entire series of nodes. And to illustrate this here is how the nodes map to each other. Is this okay? So if the blue is with 3 games left, and a win brings us to the green line and to the node. So a loss would put us here. A loss would put us back in the bankroll, so it gets us here to this node. A win would get us to this node. Right. Same thing here. So we have this nodes mapping onto other nodes, to successive nodes. So when we do this with 100 games recursively, we see how Kelly, with the 0.2 as the max, gives us a dynamic Kelly that says only when we are really, really far away from the cap do we bet the full Kelly. But as soon as we are anticipating we can make it, we drop and drop and drop and drop. And if we are really close to the cap, we are betting almost nothing. So here is the point where we propose to start. 10% of our bankroll, 10% from the max, we get 15%, 14.8 to be exact. Does anybody get 14.8? So 14.8 is where we would start. And then depending on losing or gaining, we move up or down this curve. And of course, the curve itself, just a little bit as we move closer and closer to the limit at the end of the game. All right, so the implementation again is very simple. We have a starting bankroll, a number of games to play, a maximum payout. We calculate recursively this function. Oh my wife. Yes.
We escort her out.
Yeah, really.
But I just have a question about how asymptotic that is, because
Yes.
if you want to
Right.
if you want to actually reach the maximum, at some point, you
Right.
have to bet your exact difference or half your difference or whatever, right? So
Yeah.
right? You have to, at some point, bet half your
Yeah,
difference,
and then you have to win that.
right? And then you have to win,
Yeah.
right?
Yeah, and that will
Okay,
happen
so
quite a lot.
So that'll, at some point, the fraction will be that that this tells you the bet will be that amount?
In
Okay.
fact, oh, beautiful, it's perfect. Here's a simulation that Nick programmed in R, a 3D representation of one such random walk. You see here, we start in the back. You with me there? So we start out with our bankroll being $10, we have 100 flips left, we start with a 15%, okay? And then the wind give us a little bouncy ride. You can see in this particular simulation that we had a little bit of bad luck there and we had to go even higher than 15% at one point. See that? So we may have gone to full Kelly there at this point because we dropped so far away from
So
the,
then you were below like
Yeah.
that node, and then you needed to
right,
act as if you were just doing a standard Kelly
exactly,
thing,
exactly,
starting over. Yeah,
exactly.
okay.
Okay, and then we had a bit of a lucky streak, and then eventually we were really lucky, and then got very close to the cap, and we reached the cap with 20 flips remaining. Down here, okay. So we can run that 100,000 times. Beautiful, the beauty of R and beauty of Monte Carlo simulation. In fact, Nick ran it 900,000 times. Just falling short of the million, Nick. I guess that was just basically a computational capacity here. And so here are the results. When we run the dynamic Kelly or the flex Kelly or however we want to call it, relative to the fixed Kelly, we get the following improvements. The percentage of going bust drops even another half almost from 99.99% to 0.58%. We improve the likelihood to be above water in the end from 82 to 90%. Tim, you were kind of right on here, is that we do give up a little bit in terms of how many people reach the max, right? What the likelihood is to reach the max, you give up a little bit.
It just becomes a little more asymptotic where you get really close to the max.
Yeah, it turns out that if we crank it up to 200 games, if we get to play 200 games, then even this metric is improved. So the more games you have, or the lower the cap is, then also even the percentage of reaching the max is better.
You can probably already find it in your simulation, but you could look at percent who reach 95% of the max.
Yeah, right.
And then
Right.
and that might be a better metric than who actually reaches the exact max.
Right, exactly. The average payout, that might not impress, but it's still a $20 improvement. And as expected, the average log payout, which is the metric we really want to maximize. We didn't go out to maximize the average payout, remember? But we wanted to maximize the average log payout, and our proof shows that that is the maximum possible. Also notable is that the variability in the outcomes is reduced. By basically pulling back a little bit on the Kelly, we also get a little bit less variability in the results. And therefore, we have a higher reward and a lower risk. If we put a ratio to that, a reward over risk ratio, we can see a definite improvement there as well. Now, last idea. We looked a little bit closer at this reward over risk ratio and said, we didn't set out to maximize that. So Peter, what about maximizing that, right?
Right.
So we noticed that our recursive algorithm has in it this maximum f, which was our fixed Kelly, the 2p minus 1. But what if we actually raise that a little bit? Which would be equivalent to moving from the back from the log utility back to the linear utility a little bit, which seemed justified because the cap on our game already reduces these astronomical payouts. We already have a reduction of that. So maybe moving a little bit more towards the linear utility might give us better results as far as risk and reward is concerned. And it turns out that these recursive formula I showed you earlier, we just replaced the 2p minus 1 by f max, and then see the following results. We can actually crank it all the way up to 1, like betting everything, except that, remember, that does not mean now that we're betting everything from the get-go. This is still the flex tally, saying like, okay, I can put the brakes on that F max as soon as I know that a successive number of wins would get me to the cap. So this betting going with F max equals 1 still raises our chance to go bust considerably, but it isn't 100% the way it is without the cap. And you can see that in that case, we can really maximize the average payout. And we get another nice increase from 696 to 766. And our paper shows that that also is the maximum for the expected payout under these circumstances. The best results in the other metrics remain with our original, except with the reward over risk ratio that shows a slightly better risk reward ratio when we let F max be 0.4. We do pay with a higher risk by again reaching having more a likelihood of going bust being increased, and all the other metrics go down a little bit, but the risk reward ratio has gone up. So you might ask, oh, in this case then, if I play this now, what would be my initial bet? And that Nick just told me this morning is 17%. So instead of 14.8%, about 17%. Okay, a little bit more risk friendly. So in conclusion, the fact that we have this extra information for this particular game where we are limited by a payout and limited in time, then this information can be adopted into a strategy that goes away from a fixed Cali to a flexible and functional Cali, and thereby we can improve the results by a little notch. Thank you.
So from a practical point of view, and I guess people have done this in other circumstances, you're assuming a certain utility function, basically a risk averse strategy, but a specific risk averse strategy. There's lots of different curves that could have different forms, but it goes forever, so it's easier than a lot of other ones are. But there's nothing magical about that, is there? I don't know that take a real person, they might have a slightly different utility function that would have a different result. So
I think that would be a great question. If you propose a hybrid between linear and log utility function, how then the optimal strategy would be. I don't think it would be very far away from this range we are creating here with different F maxes. Because I think of these F maxes here as sort of morphing the log utility into the linear utility function.
Unmute myself.
I'll let Andy go.
Andy, yeah?
Yes.
I don't know, Mike, would you wanna call people in from the,
Go ahead.
did
Andy.
anybody, yeah, Andy?
Yeah, so where you had the nodes, where you would, the particular graph where you're determining what to bet at each stage. You can go back to that, that was, even further back, I think. Well, maybe that's not it. Well, somewhere it is. So anyway, suppose somebody comes into the game late, right? And the amount of money that's available to them is what is the overall amount that's been computed for people who started the game. Do you follow the same curve?
Yes, the starting point is an arbitrary one. Our functions are recursively calculated for any moment in time. So you tell me the number of games remaining, you tell me what the ratio is from the max, our framework of the Kelly function, that flexible Kelly function is already computed. We compute it once and for all and then apply it to any given number of games left, to any bankroll left.
It's very strongly recursive then.
Yeah, yes, it is.
But what puzzles me about it is the first move, because it doesn't necessarily adhere to the Kelly criterion.
I think this is the curve you're talking about, right?
Probably, yeah.
So this is the function f sub 100 of
Right.
b, f sub 100 of b. And it shows that if 100 games are left, it shows what the Kelly proportion should be for any bankroll you have.
And starting at any time interval as well.
Any time interval? No, the time is the 100 right now. This graph is good for 100 games left.
I see. So I guess
If
my
there's
question
3
is,
games left, it would have this simple form. It would have this simple form. I don't have any other graphs right now. But the shape of the Kelly function does change, and it has some asymptotics. As you can imagine, if n goes greater, you can probably guess the asymptotic of that.
right,
It goes basically to 0 for all b.
yeah, if someone came in late and had had the same ending time, so they have fewer time to,
Yes.
yeah. Then I guess the curve would be the same.
No, the curve changes with every n, with every k left, with every k. We have
Yeah,
a curve every k.
I'm comparing, right, okay, yeah, I'm comparing the curve that would be obtained, say, what is the time frame? So there's a certain time frame, I don't know what it is. We'll say 1 hour.
Yeah, oh, an hour. No, we count as time the number of games left. The number of games left is what we count.
Ah, I see, okay.
I see what you're saying. Because
Yeah.
I claim that the experiment was a timed experiment, and it was.
Yeah.
And so they were slightly so if somebody could be faster, they could play more games. And that's a little complication that we didn't take into account, but the experiment did give some variability created some variability by the quickness of people's decision making and how many games they were able to play. But on average,
But most of them lost.
yeah, right. Oh, that would be interesting. The faster they played, the more likely they went bust. That's very likely true. Yes.
Well, this is a bit of an esoteric question, not being a mathematician, but is there such a thing as mathematical ethics? Because, so
Yes.
okay, I kind of expected that, but
Yes.
because there are other scenarios where you run risk and reward.
Yes.
And the immediate one that popped into my head as you were going through this talk, and I'm looking at these curves and the outcomes. And are things like when nations go to war, for example, it's an all in, it's all or nothing, right?
Oh,
And
yeah.
the outcome,
Yeah.
you're risking
Yeah.
everything, right? And would it be possible to prove that it's really not worth it? And some push and shove between nations has to occur, maybe somewhere on your curve here,
Mhm.
but that there's
So
no
that's
reason to.
Yeah, I think they're, you touch on utility again. I think basically when you're in a situation like this, the utility of your outcomes is, the weight is changed from ours. And of course, another big complication is we are assuming we know the probability of winning. We are assuming 0.6. What if we don't know that?
Well, most people going into war assume it's 100%.
Yeah, right. Well, then the math is really easy. But yeah, there's some work done in what if we know P only to a certain probability, then how would this change this? So that would be a nice follow-up research. If we know P, if we only know the distribution of P, we can make some assumptions on that, then how would this affect our chances, our strategy? I'm gonna leave this to the statisticians here. You have a comment on that?
Easy to simulate, but I don't know.
Yeah, there have been some papers written on that, what to do when P is unknown or known to only a certain degree of certainty.
Just to connect to your question, there's something called the dollar auction where it's like a normal auction, but the top bidder gets the prize and the second highest bidder has to pay their bid, whether they, no matter what. So and you can, and that was created to try to simulate a war, like say, because you're invested, you've put the money in, you're gonna lose it whether you win the war or not. And you can show under certain circumstances, that it wasn't worth it in the first place.
Interesting.
So.
Michael Posner.
That is awesome. That's an awesome comment. Yeah.
Michael Posner comments
Yeah.
that the ASA has ethical guidelines that are publicly available.
Look it up if you want to. Okay, one more question. Yes, my lovely wife.
So I have a question for Nick. Nick, are you still online?
My coworker.
Hello.
I understand, Nick, you are in the financial industry, correct?
Yes, correct.
So how would this dynamic Kelly apply in your financial industry, especially in relation to investment?
Yeah, it's a great question. And first off, thank you, Dr. Volpert, for an awesome presentation and everything. It was a wonderful representation of our work, so thank you.
Thank you.
But yeah, to answer your question, I think one of the best scenarios that I can think of, and Dr. Volpert and I have talked about this, is really goal setting and using that as your final benchmark. So you could say something like, when I retire, I want to have $1 million. And basically you can use that as your max payout and then basically time course it down. If you're, 30 and you want to retire at 60, you can use 30 years as your time. So I think that's really the most applicable kind of setup that fits our game scenario really, really tightly.
Great, thank you.
Yeah.
Questions?
Thank you all.
Have too many games left. Right, yeah, not just. They're on.
What would we do if the, goes
Half percent.
Saying, what do you?